All right, so we're going to begin today talking about carbonyl chemistry. And this is really important for understanding biology because a lot of what biology does has to do with carbonyl compounds. So we're going to be as general as possible today in terms of thinking about these compounds. Everybody see the board okay? The lights are kind of weird today. I hope we get them figured out, but people in the back can see all right-ish. Yeah, okay. Carbonyl compound, we're going to have a carbon-oxygen double bond, some R group here. This will generally be an alkyl group, perhaps a benzene ring. And then what the identity of this group that I've abbreviated Y will determine the reactivity of the compound. So what is Y usually? So sometimes it's a hydrogen. So this little squiggly line just means that this hydrogen is attached in place of the Y here. If it's a hydrogen, that would be an aldehyde. If it's like an alkyl group, or say a benzene ring, that's a ketone. And there are a lot of other alkyl groups you could think of attaching. If it's an OH group, it's a carboxylic acid. If it's an OR group, it's an ester. If it were an NH2 group or an NHR group, that would be an amide. If it were a SR group, that's a thioester. And if it were a phosphate, that would be a mixed phosphoanhydride or perhaps an acyl phosphate. And these are important intermediates in some biological reactions. But they all sort of share this same carbon-oxygen double bond. So let's talk about the things that are going to be in common among all of these types of molecules. First, the oxygen has lone pairs on it. Okay? Lone pairs are not involved in bonding. Consequently, they are higher in energy than any of the bonding orbitals. So the most reactive electrons in this molecule are the lone pairs on oxygen. If you haven't had any exposure to molecular orbitals before now, I tend to use them as ways of understanding how reactions happen. I'll post a sort of a review document on MO theory that can get you up to speed if you're struggling to understand the things I'm referring to in class about MO theory. The most reactive electrons in this molecule, another way of saying that, is what is the highest occupied molecular orbital in this molecule. What is the HOMO of the molecule? And if you do molecular orbital calculations, you will conclude that the highest energy electrons are the lone pair electrons on the oxygen. What else about carbonyl compounds? Well, you know oxygen's more electronegative than carbon, and so that adds to our conclusion that the most reactive nucleophilic part of this molecule is the carbonyl oxygen. So let's just be clear, lone pairs on oxygen are the highest occupied molecular orbital. This means that if the carbonyl compound reacts as a nucleophile, that's where it's going to react. Now, if the oxygen's more electronegative than carbon, that means there should be an electron deficient carbonyl carbon, that there should be a partial positive charge on that carbon. You can come to that conclusion as well if you consider the following resonance structure of carbonyl compounds where there's a positive charge on the carbon. From an MO perspective, where is the electrophilic spot? So based on what we've talked about in terms of electronegativity, you would say the electrophilic spot is the carbonyl carbon. What does that look like in terms of the molecular orbital theory? Well, in molecular orbital theory, the electrophilic part of a molecule is the lowest empty orbital. That's where the nucleophile will attack. That's where the next electrons can go. The lowest unoccupied molecular orbital of a carbonyl compound is the pi star, which is the carbon-oxygen antibonding orbital. And if that sounds unfamiliar to you, I'll just refer you to the MO document that I will post online. An antibonding orbital, if it's filled, the corresponding bonding orbital breaks, corresponding bond breaks. What does the pi star look like? Well, you may be familiar with, you may be more familiar with what the pi bonding orbital looks like. So let's draw this carbonyl as though we were looking at it from the side. Carbonyl carbon is sp2 hybridized trigonal planar. The pi bonding orbital is above and below the plane of the carbon-oxygen sigma bond. It has two lobes. There's a node in the middle. This is a representation of the wave function. The electron density goes to 0 for this pi bond in the plane of the page. We use color to represent different wave function signs. Wave functions are like any other function. They can have positive or negative values. To avoid confusion with positive and negative charges, we'll use color. That's a carbon-oxygen pi bonding orbital. The carbon-oxygen pi star would look like this. It would have a node in between the two atoms, the carbon and the oxygen. The node indicates that there's no electron, that if you filled this orbital, there would be no electron density in the space between the two atoms. And in fact, if you filled this orbital, electrons would be on sort of either side, tending to pull the two nuclei apart. You can tell where a node is, that is where wave function goes to 0, by places where the color switches, where the sign of the wave function switches. And molecular orbital calculations show that most of the pi star is on the carbonyl oxygen. I'm sorry, let me rephrase that. Or rather, let me correct that. Most of the pi star is on the carbonyl carbon. So if a nucleophile were to attack, it would do so at the carbonyl carbon, because that's where the available space for electrons are. We would dump electron density into that pi star, and that would break the pi bond. So that's generally how things are. That's going to be the first step of many, many, many reactions that we talk about this semester. So let's sort of talk about the patterns of reactivity that we will see for carbonyl compounds. The first, as we've just discussed, is attack of the nucleophile. I'm kind of a Star Wars nerd, so I'm imagining this as episode 2, Attack of the Nucleophile. And let's be honest, that probably would be somewhat better than the actual prequels. I don't know what your persuasion is on that. Okay, nucleophilic attack. So the key issue that we'll deal with here, in general, the nucleophile will be attacking, let's see what problem, oh, there we go. Nucleophile attacks the carbon-oxygen pi star, but the key issue is, can the nucleophile attack directly, or do we need catalysis to make it happen? Okay. We will see that strong nucleophiles attack directly. That means they go straight for the carbonyl carbon, no catalysis needed. What do we mean by strong? Well, strong is a relative term. We're going to say strong relative to a negatively charged oxygen. And we'll see why that is in just a second. How do you judge the strength of a nucleophile? Well, this is where the stuff you learned in chapter 2 from 351 comes into play. Strong nucleophiles, if it's strong relative to OR minus, it needs to be more reactive than OR minus. You know that one of the ways you can judge the strength of a base is by considering the pKa of its conjugate acid. The pKa of an alcohol is around 16. So things that can attack directly include alkoxides, but then anything that's more nucleophilic than that. Some key examples we'll see in the next little bit would be H minus. Actually, we won't use H minus directly. It'll be packaged in another form. But as a nucleophile, it's very strong. The corresponding conjugate acid is hydrogen, whose pKa is around 35. You'll see today that I'm going to be rattling off pKa's from my mind. I didn't know them before I started teaching the class. I don't expect you to have memorized them. I'll provide a pKa table for you on the exam. You should be pretty familiar with the pKa of an alcohol and also the pKa of, say, H3O plus, which is -2. Those are good sort of benchmarks. Others you can look up. This is how you can tell that H minus is more reactive than OR minus. Another example of something that can attack directly would be some kind of negatively charged carbon. Again, that's going to be packaged in a different form, which we'll talk about a little bit later, but the pKa of its conjugate acid methane is like 50. So these kinds of things will attack directly, no need for catalysis. So let's show you an example of that. Well, I'll show you what we mean by direct attack, and then I'll give you a specific example. So direct attack just involves nucleophile attacking. We break the carbon-oxygen pi bond because we've just dumped electrons from the nucleophile into the pi star. What that does is it gives us the following intermediate. This is now sp3 hybridized. We've gone from having an sp2 trigonal planar carbon to having an sp3 tetrahedral carbon, and so we will call this the tetrahedral intermediate. Notice that the tetrahedral intermediate has a negative charge on the carbon, what used to be the carbonyl oxygen. The reason it does is because we broke the carbon-oxygen pi bond and electrons moved there. That's why we're talking about the nucleophile strength relative to the negatively charged oxygen. We're basically asking what's the equilibrium constant here? Is the nucleophile more reactive or less, which is more stable, to have the negative charge on the oxygen or the negative charge on the nucleophile? And if the nucleophile is less stable than a negatively charged oxygen, why then this reaction should go forward. Okay? So that's sort of step one. A specific example of that might be, specific example of that might be, say, this aldehyde and I'm just going to use, this is an organolithium reagent. It looks like it has a covalent bond between carbon and lithium, and it sort of does, but you can think of this as basically being methyl anion. It's really not, but it reacts as though it were, and so we will draw. I did not push that button. No. We can show it reacting. We'll show electrons from this carbon-lithium bond, which we're thinking of as lone pairs on carbon, attacking the carbon-oxygen pi star, breaking the carbon-oxygen bond. That is a strong enough nucleophile to attack directly, as we've talked about, and then you get this tetrahedral intermediate. Okay? Question so far? Don't be shy. Yes?
I always wondered why it's called a carbonyl. That name doesn't make sense.
Why is it called a carbon eel? I have no idea. Good question. I got nothing. And we are basically not going to talk about nomenclature a lot. Yes, you're welcome. Because nomenclature is only useful for you in terms of understanding what we're talking about in class. In terms of naming a molecule, for the most part, if molecules are more complicated than some of the stuff we're drawing here, we'll call it compound 1, compound 2 in our papers because we're lazy. So, all right. Other questions? Yes?
So basically we're looking at the nucleophile and then at the nucleophile, and then what would happen if the nucleophile attacked the carbonyl. Whichever one is, if the nucleophile is more stable, then it's probably not going to go through the attack.
That's right. If the nucleophile is more stable than a negatively charged oxygen, then direct attack is probably not going to happen. Okay? Yes?
You said something about the hydrogen, how it wouldn't work or something. You said the hydrogen is a low in H, has a higher pKa, so it would be a good nucleophile, but you said it's going to be disguised as something else.
I think I said that for a negatively charged hydrogen and for a negatively charged carbon, we're not really going to use those as reagents. They will come packaged in another form, which we'll talk about later. I think that was it. What else? Yeah.
So when can you use an alcohol as the reagent if either way an oxygen is going to bear the negative charge? Like why would that reaction proceed?
Well, yes, good question. So the question is, what if, say, you're using as a nucleophile a negatively charged oxygen? Is it reasonable for that negatively charged oxygen to attack to give you this tetrahedral intermediate? And again, the issue is really, what's this equilibrium constant? I don't know why that happened. I'm sorry about that. Why am I getting emails? Close. There we go. Sorry. Yeah, so the issue is really, what is this equilibrium constant? And if it's around 1 or greater, then it's a reasonable step. So yeah, I agree with you that this is probably not as favorable forward as, say, this reaction is, because a negatively charged carbon is way less stable than a negatively charged oxygen. Okay, what else? But yeah, the key issue here will be, can we make an appreciable amount of this? And then we're going to talk about what happens next, and that can influence the course of the reaction. Yeah?
And what kind of constant? Sorry, I didn't hear it quite. What's the constant we're looking for to be about around 1?
Oh, well, yeah, I'm not defining equilibrium constants. I'm not going to ask you to predict what the numbers are. We're basically just saying, is the reaction favorable in the forward direction? And basically, if it's about 50-50, that's good enough. Okay, what else? All right. So let's talk about weaker nucleophiles. Weaker nucleophiles, again, that's relative to negatively charged oxygen. Weaker nucleophiles need help in the form of catalysis to make the reaction go. What do we mean by weaker? Well, these would be nucleophiles whose conjugate acids have pKa's less than 16. So examples of these include water or alcohols, amines like ammonia or primary or secondary amines, CN minus. All of these are nucleophiles, and if you draw their conjugate acids, they have pKa's that are less than 16. It's -2 for the alcohol, for the hydronium, for the protonated alcohol. It's in the range of 9 to 11 for amino groups like ammonium, or this primary ammonium, HCN has a pK of about 9. So these are things that are not as reactive as a negatively charged oxygen, where if we considered this equilibrium nucleophile attacking, we might say, yeah, probably not. Probably starting materials are favored. So how do we make that happen? We use catalysis. And usually this is acid catalysis. And this comes in a couple of flavors. The first, and I'm not going to ask you to memorize what these are called, but I want to give you a couple of options and have you be familiar with both. Specific acid catalysis. And what happens here is we take our carbonyl compound, and in a first step, we add acid, and the nucleophile is, in this case, our carbonyl compound, and the reactive electrons are the lone pair electrons. So they will attack the proton in the acid, and you will generate this protonated oxonium ion. Now, the oxonium ion is now more reactive than the carbonyl. You can tell it's more reactive for a couple of reasons. First, you have a positive charge, positive formal charge on the carbonyl oxygen, but resonance tells you that resonance and consideration of oxygen's electronegativity relative to carbon tells you a big part of that positive charge is now on the carbonyl carbon. So it's more electrophilic. Another way of viewing this is that adding protonating the carbonyl oxygen lowers the energy of the carbon-oxygen pi star and makes it more accessible to nucleophiles. So you protonate to make the carbonyl compound more reactive, and then in a second step, the nucleophile attacks. Usually the protonation is fast, and then usually nucleophilic attack is slower, and you get a tetrahedral intermediate, and it only differs from the tetrahedral intermediate that we saw previously in that the oxygen's not negatively charged. So this is how we get around the issue of using nucleophiles that are less reactive than a negatively charged oxygen. We make it so the tetrahedral intermediate doesn't have a negatively charged oxygen, and that makes the equilibrium more favorable. Okay, questions about that? Yeah?
And when you say slow, does that mean that like it's slower than the step where it's just a direct attack?
Is it slower than the step where it's just direct attack? No, because remember, for these weak nucleophiles, direct attack is so slow it doesn't happen.
Okay.
Yeah. And slow and fast are relative. This is actually really kind of complicated. There's a whole branch of organic chemistry that studies mechanisms and does kinetic measurements, so we're not even going to really get into that. Other questions? Yeah.
If we're doing it this way, will we always end up with that hydrogen on the oxygen, or are we going to end up taking that off later?
Will we always end up with the hydrogen on the oxygen, or will we take it off later? It will depend. So right now we're talking about what the nucleophile attacking. Sort of step 2 is going to be what happens to the tetrahedral intermediate. And so we'll deal with that. What else? Yeah?
Sorry, I know you addressed this already, but what does the blue highlight mean again?
What does the blue highlight mean again? I don't know. I think I'm using it for the carbonyl oxygen.
Okay.
In the tetrahedral intermediate that you get after direct attack, that's negatively charged. Here we add the proton first, and then we don't have a negatively charged tetrahedral intermediate. Yeah. Okay. So there's another version of this called, okay, why are we struggling here? Trying to zoom in and out, and the iPad's being slow. Another form of acid catalysis is called general acid catalysis. It's so lame, but I always think general acid catalysis, reporting for duty. And you don't need to know why one's called specific versus general. That part's actually maddening, and they'll maybe try to describe it for you in biochem, and you can worry about it then. In general acid catalysis, the protonation step and the nucleophile attacking step are similar in fastness, and they actually occur, similar in speed, and they actually occur at the same time. So you'll have the nucleophile attack, and at the same time you break the carbon-oxygen pi bond, electrons move up onto oxygen, and then at the same time lone pair electrons on the oxygen attack the hydrogen, and the A group leaves, and that gets us directly to that neutral tetrahedral intermediate and I guess the conjugate base of our acid. Which happens when? Actually, that's a subtle issue that has to deal with the identity of the nucleophile and the strength of the acid. We're not going to navigate that at all. We won't worry about that. You're going to see in various mechanisms that the Smith text presents to you. A lot of times you'll see specific acid catalysis. Sometimes, to save time because we're tired of drawing intermediates, we'll show it all in one step. Understand that we're going to be basically agnostic about which of these two options it is. As long as you understand that both are possibilities, that's good enough for us right now. Okay? So, if the nucleophile is weak, you got to protonate the carbonyl oxygen first. Questions? Yeah?
So could either happen in 2 steps or 1 step? Is that what we're saying?
Yeah, the difference between these two is fast protonation step followed by slow addition step, nucleophile adding, versus concerted all at once. Yeah. I apologize for the quality of my voice. It's kind of grating, so I'm sorry I'm hoarse. Go ahead.
You said if it's weak to protein at first. What do you mean if what's weak? ROI?
Can you say that one more time? I didn't
You
catch
said
all of it.
if something is weak, it's protein at first.
Right, if we use a weak nucleophile, the nucleophile can't attack directly. We either need to protonate the oxygen first or during nucleophilic attack. All right, so let's talk about the fate of the tetrahedral intermediate. That sounds epic. Okay, so what happens once you have a tetrahedral intermediate? So recall, and we'll deal with the negatively charged one first. Our tetrahedral intermediate looks like this. We have a nucleophile, and we have the R group, and we have a negatively charged oxygen. And what happens next is going to depend on a consideration of all 3 of these groups. Okay? We're going to ask about the leaving group ability, leaving group goodness of Y minus and or the nucleophile. Okay? Is Y minus a better leaving group than the nucleophile, or is the nucleophile a better leaving group than Y minus? Of course, leaving group ability is relative, so the question is relative to what? And the answer is going to be, again, relative to a negatively charged oxygen. I'll show you why that's the case in a little bit. To talk about what happens next, it's useful to make a connection with something you learned in 351. You did elimination reactions where you have a leaving group here. We'll call the carbon that bears the leaving group the alpha carbon. The one adjacent to it is a beta carbon. And you've before done reactions where a base removes the beta proton. Then the electrons from that carbon-hydrogen bond go here to become a new pi bond, and the leaving group leaves. In terms of molecular orbital theory, what's going on here is that the electrons in this carbon-hydrogen bond are dumping into the carbon leaving group antibonding orbital, or sigma star, breaking that bond and creating a new pi bond. But the idea here is that if you have electrons adjacent or beta to a leaving group, you can do an elimination reaction. And that's called sometimes, you probably didn't call it this in 351, but it's sometimes called beta elimination. Now, if you look at that tetrahedral intermediate, we have a similar situation. We have a carbon that's attached to a leaving group, and then we have an oxygen with a negative charge on it, lone pairs on that oxygen adjacent to the leaving group. So we're in almost the same situation. It would be if you imagine that proton being removed first, and there are examples of elimination reactions that are that way, and then this happens. That's the exact analogy that we're dealing with here. Can these electrons on the negatively charged oxygen do beta elimination to kick off the leaving group? Okay, that's sort of what we're asking. So let's deal with a couple of specific cases, all right? So case A, I suppose, is where Y is a good leaving group relative to the negatively charged oxygen and is also a better leaving group than the nucleophile. Sorry about penmanship. Sometimes when I'm writing quickly, it gets a little messy. Of course, some of you want to be physicians anyway, so being able to read messy writing is, I don't know, things are all on computers, so maybe the day of the prescription written by a physician that nobody can read is over. I don't know. Okay, so let's suppose that Y is a good leaving group relative to the nucleophile, and a good leaving group relative to a negatively charged oxygen. Then it's reasonable to imagine electrons on that oxygen kicking down into the carbon leaving group antibonding orbital. Leaving group leaves, and you end up with the following product where the nucleophile is present in place of the Y group. And hopefully this illustrates why we care about how good the Y group is as a leaving group relative to the negatively charged oxygen, right? Because we're basically asking about this equilibrium. Which is better, to have a negatively charged oxygen or to kick the Y group off and have the negative charge on the Y group? Okay? So let me give you a specific example of, and if you look overall where we started, and we add the nucleophile, this gives us what's called a substitution product. Apple Pencil battery is low, 5%, 10 minutes left, we're good. Substitution. I tried charging it before class, but apparently it didn't work. This reaction is often called nucleophilic acyl substitution. It's really important if you've ever taken, let's see what, I think it's aspirin has functions because of nucleophilic acyl substitution. Some beta-lactam antibiotics work by nucleophilic acyl substitution. I'll show you examples of those later, but basically we're swapping out the Y group for the nucleophile. But unlike SN2 reactions, this doesn't happen in one step. It happens via addition of the nucleophile and then elimination of the leaving group. Okay? And a classic example of that would be if the Y group is Cl minus, and let's suppose the nucleophile is this alkoxide. That would add directly to the carbonyl carbon to give you the tetrahedral intermediate. Then once you're there, you compare the leaving group ability of the alkoxide versus that of chloride. You may already know that, but if you don't, simply draw both of them as they would look if they left. Then draw the conjugate acid. Then go look up the conjugate acid pKa, minus 9 and 16. So it's no contest. Cl minus is the better leaving group. Lone pair electrons kick down and Cl minus leaves to give us the substitution product, which is, in this case, an ester. Okay? Now you're going to be tempted to try to memorize things at some point when we give specific reactions. You may be tempted to sort of have a mantra that alkoxides react with acid chlorides to give esters. Which you can do, but it's pointless because if you understand these basic reactivity patterns, the product follows obviously from the starting materials and the reagents if you understand the principles. All right, questions about that? Yes?
So if we're comparing the two conjugate acids, the conjugate acid with the lower pK, or with the lower pKa is going to be the
Better leaving
leaving
group.
group?
Yeah. Yes, the leaving group whose conjugate acid has the lowest pKa is the best leaving group. Yeah.
So with the product of this next reaction, you could theoretically start another, like nucleophilic attack, substitution, that kind of stuff over and over again?
Right. Could you, yeah, it's a great question. Could you then have this product react? And the answer is yes, you can do separate things with this. One question is, if you have any leftover alkoxide, does that alkoxide attack? And I'd say, sure, that's reasonable, but then look what happens here. You get to a tetrahedral intermediate, and that negatively charged oxygen, you can just kick the other alkoxide right off. And so, so you can't actually tell that that's happening. All right.
I have a question.
Yeah, go ahead.
If there's like a hydrogen present, when there's that negatively charged oxygen, would it just make like an OH group instead of bumping off one of the other groups?
If there's a hydrogen instead of, so you're talking about this situation?
Yeah.
Okay. Same considerations here for the neutral tetrahedral intermediate. Let me show you a case where the Y group would be good enough to leave. If the Y group were, say, hydronium, then you ask which is better, to have a positive charge on oxygen or a positive charge on oxygen. Comparatively, they're sort of the same. So when you have a neutral oxygen, your standard for leaving group goodness adjusts. It has to be at least as good of a leaving group as water. Okay. So let's talk about situation B. And situation B is where Y minus is not a good leaving group relative to a negatively charged oxygen, and is also a poorer leaving group than, yeah, I think that's good enough. Or alternatively, the Y- and the nucleophile are both not good leaving groups relative to the negatively charged oxygen. What happens then when you get to the tetrahedral intermediate, that negatively charged oxygen is not reactive enough to kick off either the leaving group Y or the nucleophile, so you are stuck and the reaction is done until you work the reaction up. Now in the lab, when you go to run a reaction, you do it and then you need to isolate the products and purify them. We typically don't worry about that in this class. If you take the lab 353, you probably will get to do some of that. One of the parts of isolating your final product involves what's called aqueous workup. You basically dump water in your reaction. What that would do here is simply protonate the carbonyl oxygen, protonate the oxygen of the tetrahedral intermediate, and you get this product. Now notice how this product differs from the substitution product that we got earlier. This is simply an addition product. We added the nucleophile, but we didn't lose the leaving group, and all that happened is that after the reaction, we did an aqueous workup step and we got the alcohol. Okay, let me give you an example of this. Suppose, suppose our starting material was an aldehyde, and suppose our nucleophile was an organolithium reagent. This is, remember, functions just like a negatively charged carbon. Those electrons attack the pi star. We break the pi bond. We get to a tetrahedral intermediate. That is the addition step. That's the attack of the nucleophile step. Here's the tetrahedral intermediate. We're going to compare the nucleophile and the Y group relative to a negatively charged oxygen. And again, if you are struggling to make that comparison, just draw the two groups as they would be if they left, then write down their conjugate acids, and then look up the relevant pKa's, which are, I believe, 35 and 50. Then draw a negatively charged oxygen and look at the pKa of its conjugate acid, and you can see very clearly that these two leaving groups are, well, these two groups, the CH3 and the H, are terrible leaving groups relative to a negatively charged oxygen. You cannot do the beta elimination step. That negatively charged oxygen is not strong enough to kick off stuck, sorry. Not strong enough to kick off H- or CH3-. So you are stuck there until aqueous workup, wherein you will add water, and that allows you to protonate the negatively charged oxygen. Usually you're adding not only water, but some kind of buffer that will bring everything to its preferred protonation state. And that gives you this secondary alcohol. Okay. Now, you're again going to be tempted when we get there to memorize that aldehydes react with organolithium reagents to give you secondary alcohols. And then maybe hit yourself with your book or something like that. It's a Monty Python. But you don't need to, because that conclusion is obvious given the starting material and the reagent if you understand about leaving groups and if you understand these reactivity patterns. So you're going to need to do some memorization in this class, and nothing's going to save you from forgetting what a reagent is, but the reactivity patterns are going to help you remember what happens. The last situation I think we're going to talk about today is the dumb situation, wherein the nucleophile is a better leaving group than the thing that's already there. Okay? So just imagine you have a tetrahedral intermediate that looks like this. Okay, first, I'm going to have to ask you to suspend disbelief because I've already told you that this won't happen. Right? Cl minus is not a good nucleophile to attack and generate a negatively charged oxygen. We've already talked about that. But if it did happen, and this is one of the reasons why we don't consider it, if it did happen, this is the Y group, this is your nucleophile. Which is the better leaving group there? Cl minus, and so the thing you added is just going to get kicked right off. And it's as though it never happened. What we're basically saying is what we've shown you here is another reason why Cl minus can't attack directly, because the tetrahedral intermediate isn't stable and would go right back to the starting materials. Later on, you're going to see the text say something like, you can't synthesize an acid chloride directly from an ester. This is why. All right, that's it. I will see you Wednesday.